Let's look at the agenda. And welcome to the second day of our introduction to Julia for high performance computing. Today we're gonna talk about performance optimization. Therefore, if we still look at applications in our code that's running on only one thread, we can analyze and measure the performance and see where we can improve something. So that's what I'm going to talk about this morning. And then in the afternoon, Shin will talk about multi-threading, where we're going to parallelize our code still on one machine, but on to multiple cores. Do you have any questions? No? We can dive right in. So what we're going to look at now is the performance engineering approach. So a methodology to improve the performance. We're looking at benchmarks, how to measure things, memory allocations, and the memory layout, which is an important topic for any application, not just in Julia. And we're going to take a closer look at the hardware that our applications are running on, in this case, the cluster hardware, and how it influences the performance. Now, the performance engineering process. So the idea is not simply fiddle around with the code and hope that it's gonna help your performance, but first do an informed decision about where to change your code in what way. So the idea is you first do measurements to figure out which are the pain points in your code, which take a long time in your runtime, and then analyze these places and see which places of your code are worth taking a look into, worth investing time in optimizing, and this way guide your optimization. So the easiest thing to measure is just the runtime. You start at the beginning and at the stop. So, or you could also measure the energy. So there is you can measure different things and optimize for different things. And at the start, we can do one measurement as a baseline and see where do we start, which is what is the performance of our current code. And then we identify these intensive regions. And then we can do more precise profiling of these code regions to understand how they perform and what to improve. We can also measure different metrics to understand how do they behave. How do these code regions behave, and why is maybe their performance not as optimal as we want to. Therefore, we have a loop of measuring the current state. We're getting some metrics, some numbers out, and then we can analyze what we've measured and optimize our code. And then we can measure again and compare and see if it helped. So here's an example. We can start with a baseline and then do some algorithmic optimizations. For example, avoid some redundant calculations. If you calculate it once and then just reuse the result, maybe it will be faster. And maybe we get an improvement or speed up of 1.7. Then we can take a look into further single core optimization, maybe So in this case, for C or Fortran, we can take a look at compiler options, maybe. And maybe there's also an optimization. We try to improve on memory patterns, but maybe it will make the code too complicated, too involved, and it's not really worth it. And then one can also look into going into multi-core parallelization. What if we do a parallelized version and let it run on multiple cores to reduce the runtime of our application? And maybe then we also figure out that there's some synchronization problem, there's some locks that's stopping our program, so it has to wait a long time between the cores. And then maybe one could improve that and achieve also a speed up there. So this could be a journey of different steps of optimization where you measure, do an optimization measure again, and see what improved. Now, measurement in itself is, so there are some caveats, some things where you have to look out for. And here's an example of an application where we are computing pi. So there's one method of computing pi where we just take random points in a plane and then check if these points are inside our circle or not. So this is a probabilistic approach. So the code is quite easy. We just decide on how many samples we take. And this also decides how good our measurement of pi will be. And here we see that we take just some random numbers, two numbers for the coordinates, x and y, and then we check the distance to the center. And if it's smaller than 1, it's just inside of the circle, and we count it as a hit. And with a higher number of points, we get therefore a higher precision of our estimation of pi. Now what we can do is we can do a simple time measurement. So there's the add time macro in Julia. And what we will see is if we do one measurement, it will have some time of 0.15 seconds. But the first time is always somewhat slower. We also see it here in the output. There's a certain portion of this time spent on the compilation. And so the first execution in Julia of a function, because of this compilation step, is not representative. Therefore, in the benchmark, you will always want to do multiple measurements to also have to see the runtime variations and see what variance you have in your measurements. So we see there are maybe some outliers if you do it multiple times. Therefore, it's not sufficient to have only one measurement of your runtime. So if we are measuring our code, we have to look out for the smallest amount that we can actually measure. So if we take a time in our computer then we have to check on the current clock of our computer. And this has only a certain precision. Therefore, if we measure too narrow or too short time frames, then there will be a certain variance just from the clock itself. It's not precise enough to measure these events. Therefore, the thing that we are measuring has to be large enough. We can, for example, if this is not the case, we can, for example, look at larger inputs or do the thing that we want to measure in the loop just to extend the time frame that we measure so it will be more accurate. Next thing is we want to measure the relevant parts. For example, if you have an application that first has to read some data and at the end also has to write them, then this will have an impact on your measurement if you only want to measure the computation itself. And there will be also introduced variance. If you write files, maybe sometimes it waits for the disk, sometimes it doesn't. So it has an influence on your measurement. You don't want that. Therefore, you want to identify the thing that you want to measure and make sure that you only measure this relevant part. Also, for example, if you have some debugging output with your logging, that also often takes time. Maybe you want to turn this off for your measurement. And there can be some sources of noise, background processes on your computer that influence the measurement. And then you get sources of variance in your measurement that hinders your interpretation of what you measured. Therefore, that was also the reason if you do measurements on the cluster, you would allocate one complete node exclusively, just so no other job influences the performance of your application of your code. And then if we are measuring multiple times, we can then take a closer look. We can plot it. There are different plots that highlight different things to help you understand your measurements. You can have just a scatter plot where every point is one sample, but you see there's some overlap and you don't have a good look at the proportions. Or if you have a box plot, then you can, there is the quartiles here rendered, but in a violin plot, you maybe have a better idea of the shape of the distribution of your samples and so on. So you can do multiple plots to understand your measurements. So we have our usual statistical numbers for a distribution, the mean, the median, minimum, max, standard deviation, and so on, that can help you understand the data. But it's also always helpful to simply not only look at these numbers, but look at the shape of your distribution, or also just plot the scatter plot or violin plot.
They give me like how you make the select like so you have to run like I don't know 100 times 2 minutes to run
Well, if the computation takes a long time and you would always want to run it multiple times for a good view on what is happening, maybe you have to figure out if you can reduce what you want to measure. Or you can think about how to reduce the input, maybe do less loops inside of what you're measuring to reduce the time. But this is a question of, so in the end, our goal is to improve the performance of our application. And if we change what we are running for the benchmark, then we also change how representative the benchmark is for what we actually want to run in the end. Therefore, sometimes it's good. We only take one piece of code that's maybe the hot loop of our algorithm, and then we measure that and then figure out what is happening, and then we can improve it, and this will also improve the complete application. But this is something that we have to be clear about, that benchmark has to be representative. And if we change what we are measuring, then maybe it's not representative anymore. So usually it's fine. We know it's our simulation has 100,000 iterations. Maybe we only need 100 iterations to get a good view, and then we can run these 100 iterations multiple times and then measure that. And then if we improve that, then this will also improve the complete application. So if it's really taking 15 minutes, maybe then you can let it benchmark overnight.
Want to see roughly how long it takes, right? Like you run it overnight, and after that, the information is that like one run takes 15 minutes, and then at the end you get the mean. It was like 17 minutes. Let's say like this. Like, so does it really worse to do that amount of before? Like, is it that valuable the wrong or like,
Well, if some runtimes of your application take 10 minutes and then in the mean it will take 17 minutes, and then maybe in the maximum it will be twice as long or thrice as long, then maybe there is a source for this variance that it's worth looking into. Why is this variance so large? Why is it sometimes taking twice or thrice as long as in the best case? And then to improve the performance, you can then further investigate where this variance is coming from. And if you can remove the source of the variance, then you could also make sure that it's always the best case. And if in the end you can make sure that it's always running 3 times as fast, it's always an investment of time for the investigation and to improve the performance. Hey, let's take a look. So I have here the Compute Pi application. And we can measure it. And just as before, we have a certain variance here in the values. We can do it sometimes or have more samples that we can plot. And then we can do some plots for all of our values. Now it's loading importing the plot. And we can already see that we had one outlier with 80 milliseconds, but then we also see there's some kind of a certain variance. It looks like two blocks here. So we see here our two bulges. Now there's also a nice package called BenchmarkTools that will run our function. It will make sure that the first run is already fine. So as explained, the first execution has always this compilation overhead, and it will do in this case 123 samples. What it does is it looks of how long does it take to do the first sample of the execution, and then do some estimation how many executions it wants to do to have a reasonable amount of samples. Therefore, if the first sample takes like 5 minutes, it maybe is only doing one. But if it's like in this case, only maybe 40 milliseconds, then it will do some more samples to get a nice distribution, and it prints it here in the histogram. We see our measurements. So this is then more convenient than do this yourself. So this is a nice way. And it already also gives you then the mean, median, min, max values. Mm. In the package, there are also some replacements for the normal time. So we instead of time and elapsed, we also have b time and b elapsed that are doing the thing that is also the benchmark doing, but only returns one value. So this could be a nice replacement if you just need to one value, or you can just do the benchmark macro. Now, if we are running a function and passing some parameters, maybe you don't want these include the creation of these parameters. You don't want to include these in your actual benchmark. Therefore, you could create some variables, then assign the values to them, and then do the benchmark. Or this macro also has a feature where you can put a $sign around some portions here, and then it will make sure to first execute these input operations, get the input data, and then the benchmark itself will not include this preparation work. So in this case, it's then called interpolation with the $sign, which is quite handy. The only thing is sometimes it's interpreted by the macro, and some other macros don't like these and then don't understand it. But this is also a point you have to make sure that this preparation work is not included in your benchmark if you want to benchmark only the function itself. There are also some other parameters to the benchmark. You can just also tell it how many samples to do. There's also this setup parameter where you can explicitly run some code for the setup of the benchmark. And as explained, there is a certain variance also included through your benchmark itself. So in general, every measurement also has certain influence on your code. And it really depends on what exactly is measured. So sometimes measurements will do some sampling in while your code is running. Depends on what exactly you are doing with profiling and so on. And then this will have an influence on the performance of your benchmark. Therefore, you have to look out for that a measurement is always also somehow influencing the execution. If you're just measuring time, therefore getting the current clock before your code and then afterwards, then it's not so dramatic. But for some other measurements, it may be different. Yes, and only measure the relevant parts. Now, what we can also do is we've measured our compute_pi function with one certain parameter. Therefore, with one number of with one number of samples that we do in our loop of compute_pi. What we can also do, we can measure it with a range of numbers to see how it will behave if we change our input value. And here we see if we just measure it with a range of iterations, then we can also investigate of how the input parameter influences the performance of our application. So here we see that we have a certain dependence. Obviously, if we do more iterations, then our loop has to has more iterations, therefore it takes longer. But we also see there's a certain variance in the runtime depending on these iterations. Now, if we just do the normal at time, it will also tell us something about the allocations. And now this is the topic of memory allocations, which have a very large impact on the performance. We do it once with 1024 and with 2048, and we see that in one case we have 2000 allocations, and in the other case 4000 allocations. And these are quite a lot of allocations just to have a little loop. Therefore, we have allocations that depend on the number of iterations in our loop. And this is quite an overhead for our performance. What you usually want to do is, if you need some allocations, do some allocations before to have the memory, and then you have your hot loop that is just doing some computations. And then you don't have all the allocations inside of your loop because this slows down the loop. Now, if we look closer, then we figure out that so there is profiling in Julia for memory allocations. So this is one way to profile. It's quite small. Here we go. There are multiple ways to profile things in Julia. There's also memory allocation profiling. So I have here a link into the documentation that explains how to do more extensive profiling. In this case, I'm using this way where I'm starting Julia with this track allocation parameter, and it will then generate a text file that shows where the allocations are happening in our code when it is executing the script. And as we see here, this is the place where these allocations are done. And then they are done implicitly. So it's not immediately visible what's happening. But apparently, if we're running rand to generate a random number, if we tell it to generate multiple numbers, it will say, okay, I will create an array for you with these multiple numbers. And then it will return the array. And then we will expand the array again into two values. So if you do it once in our application, maybe that's fine. But in our hot loop, to do it all the time, that's not a good idea. Now, what are allocations anyway? So there are two kinds of memory allocations in general in applications. One, the first kind is memory allocations on the stack. So what's the stack? If we run a computer program with multiple functions, then one function is calling a different function and so on. For example, here we have our main function and it's calling foo, and then foo is calling bar, and bar has some variables, some local variables. Then we have to store them somewhere in memory. And we have to remember the order of the functions that were called. Therefore, if bar returns, then Julia knows that it has to go back into the foo function. And this is done with the stack. And the stack is a piece of memory that has a start and an end, and it has a pointer in the middle. And then Julia can put some memory on top of it. Then the pointer will be increased, and it can remove it again, and then it can decrease the pointer again. So in this case, we see that there is an entry for the main function, then the foo function was called, then the bar function, then the bar function is doing something with local variables, therefore it can store them on the stack, do something with them, and then when bar returns, it can, for example, remove or put the stack pointer back here after foo. Then it's still in memory, so it's not really deleted, but because the pointer was moved, we basically forget about this data, and then the return value can be returned, and Julia then knows I have to continue with the foo function and do something with the return value. And the stack allocation is very fast because you know where the pointer is. If you need a place to store your data in memory, you can just change the pointer, and you have a place for your data. So it has a very low overhead of managing this structure. And this is then used for temporary data. The other kind of memory allocation is memory allocation on the heap. And this is a place in a different corner of the memory. And here this is used for more dynamic data that is large. If you create a large array where some stuff is changed and then is passed to different functions and so on, then you don't want to have it on the stack. You want to have it in this heap. And here you have more overhead in managing this heap. Therefore, you have some algorithms there that have some data structures that try to control, okay, I need now a 5 megabyte array, then, okay, here's some free spaces. It will be here, or I need a 5 gigabyte array, then it won't fit in here. It has to go somewhere else. And this creates some overhead because you want for efficiency reasons in the memory, you don't want to have you basically want to sort these allocations so you have less fragmentation. And it can also be that at a certain moment in time, Julia doesn't have enough free memory, then it has to ask the operating system for more memory, and then this takes even more time than just managing of these data structures. And then the garbage collector also has to clean up regularly some memory that is not needed anymore. So we use this heap, or Julia uses the heap for large data, or if you pass data in between function calls, then it can't stay on the stack because the stack, if the function returns, is cleaned up. And also for unpredictable data structures. If you have a data structure where you can add some data, then it has to manage it, and this can't happen on the stack. Therefore, we see that for the stack allocation, there's a small overhead, and but the stack size isn't that large. And for the heap allocation, there's a larger overhead, and it's only limited by the free system memory. And so we figured out by profiling, by do a measurement on our example code where the allocations are happening. And we can write some different code. And this time, in this case, we simply do two rand calls. And rand, in this case, will not create an array. Therefore, it will not do an allocation. And we just get the two random values. And as we see here, there's a different picture here. With the blue is our old measurement for different iterations. And here in the red, this is the new one. And it's way faster, and it has a way lower variance, because this variance then comes from certain other factors in how the heap data structures currently and what state it is. Maybe it then needs some more time to clean something up, or it even pardon?
Sorry, I don't understand why is saved now in heap. The other one is saved in stack.
Exactly, it is hard to understand. So what are the reasons, or when will Julia use the stack, and when will it use the heap? So these depend on the concrete Julia version, because Julia has to, in the compilation, if Julia compiles the function, it has to decide, okay, this piece of memory, do I need to create an allocation on the heap, or can I put it on the stack? And since the stack is preferable, but has some restrictions, the Julia compiler has basically to prove that it is safe to do the stack allocation, and not put it on the heap where it would have would have more overhead. Therefore, it has to prove that these requirements are fulfilled. So the data has to fit on the stack. If you're doing a 5 gigabit array, then it won't fit in the stack. So it has to put it on the heap. Or if the data is referenced only while your function is going on. So if you pass the data somewhere else to a different function, or maybe do some I/O thing where it has to make sure that even if my function is returning, it's still accessible. It can't be put on the stack, because it could be overwritten by the stack is then used by other functions. So it has go to the heap. Also, the data has to have a fixed size, because once it's on the stack, the pointers increased, and maybe something else is also afterwards coming on the stack, and then this data can't be changed in the size anymore. And the data should be immutable, or and there it's so these are some requirements, but it's not always clear if Julia can prove them. So if you look at it from a human perspective, it could also be that Julia is doing some crazy optimization, and then it works out, even if it looks like it shouldn't work because one of the requirements is not fulfilled. But maybe Julia can do some optimization, and then internally it changes the code, and then it will work.
Can you check which, like, if the data is stored on the stack or on the heap, or if memory allocation has been made on the heap compared to on the stack?
Well, we did it with the stack allocation thing, or you can, if you're using time, we also saw that here on the bottom you see time will also show how many allocations were done and the size.
But like these allocations, does it include both allocations on the heap and on the stack, or only on the heap?
Okay, no, in this case it only means heap allocations because
okay.
No.
Okay, thank you.
Therefore, it's then very useful to do the measurement, so you understand what is happening, where are the allocations coming from, and how can you circumvent them. Okay, this is the... Okay, let's take a look at another example. Here we have, here the idea is that we have an image, and an image is often consists of pixels, and a pixel has multiple colors. So we have, for the first pixel, we have 3 color values. And then for the next pixel, again, 3 color values, but we can store them after each other sequentially in the array. Therefore, we can represent our image just as values in an array. And now the idea is we have an array of our values, and we want to turn our picture to grayscale. And how do we do this? If we have the 3 values of our pixel, we can just take the mean of our 3 color values, then set all the 3 values to the mean value, and then it will be basically a gray value because all color components are have the same value. And in this case, we have our inner function gray, which turns 1 pixel to the gray value, and we have our fade to gray function that takes an array, loops over the array, and then just calls the gray function. And if we want to overwrite our input array, and if we measure this, we will also see that it takes some time. We have a certain shape in our distribution. So many samples are here on the 900 microseconds range, but it also can go up to 1.6 milliseconds. And we see that we have 40,000 allocations, which is quite a lot just to iterate over an array and put the turn the pixels to gray, basically. And as you see here, also this note, for this example, I had to say no inline. Inlining means that if Julia compiles this fade to gray function, it will see that this other function that's called gray is small, and it can be just inlined, included into the fade to gray. And this would enable some of the optimization that I've talked about. But for this example case, I said no inline, so it won't be inlined. It will be a real function call. And then Julia has a harder time to prove these requirements. And then we see that there are some allocations done. Now, if we measure it again with the same method, we see that there are some allocations in our inner function because we're returning an array, we are creating an array, and arrays are often or usually put into the heap because arrays are mutable, they can change in size, and here we are even explicitly are creating an array to return the values. But we also see here for the input parameter of our gray function, there's also an array allocation for our pixel. We took the 3 values and then this created a new array that is passed to the gray function. So we have 2 places where allocations are happening. And we can think about how to remove them. So one idea is to use a tuple if we return the values. And tuples, as explained, they are immutable and they always have a fixed size. Therefore, it's far easier for Julia to just put them on the stack because Julia knows it won't be changed. It only needs a fixed amount of space on the stack. And if we are, when we are passing the pixel to our gray function, we are creating a view. Now, a view is a method in Julia to create a new array, but it's not really a new array. It is just a view of our existing array. So it behaves like a smaller version of the array. So we decide, specify what portion of our original array we want to look at. And then it creates this view that works as an array, but we do not need additional memory for that. We just need the reference basically to the old one. And this is also what we want to do. If we pass this data, we don't really need to copy the data out of the array. We just need the original values, and these can be accessed through the view. And if you do that, we see that in our example, we have a far better performance and no allocations anymore. Okay, here is a before-after comparison. And we also see that in the old version, we had some garbage collector activity, and this is also gone from the new version. So the garbage collector will then make sure to clean up some unneeded memory from the heap in the background. And since we are at it, we can also do some other improvements. For example, we don't necessarily need to return the values to change them. We can also make the inner function themselves overwrite the values in the array. So we can just pass the view, and then it looks like it's an array with 3 values, and we can overwrite these values in the array. And here then there's a little bit less of data being copied on the stack and so on. So it's a little bit better. As we've seen, it's important for Julia to know if the size of our data changes or not. And there is a package called static arrays, which creates arrays or things that behave like arrays, but it can guarantee that the size does not change. Internally, it's using tuples. It's but it helps Julia to optimize certain things. And it has it's quite convenient to use. And in some situations, it can help the performance by making sure that Julia can optimize things because it can prove that the size of the data structure will never change. Another thing is the broadcasting or dot operator. And in this example here, we have three vectors. And we are benchmarking this little expression, 6 times the vector plus 3 times the b vector plus 5 times the c vector. And then everything is added. And if we measure this, we see that there are some allocations done, because if we first do the first expression, then there has to be some temporary allocation be done for the temporary values. And this is then also true for the other sub-expressions here. And then everything has to be added and so on. So it's basically is doing first the first thing, then the second thing, then it adds everything up after each other, and then it has to store these intermediate values somewhere. Now, a different way would be, what if we do not do this vector-wise for the complete vector, but element-wise of the vectors? And this is what the dot operator is doing. If you're using this dot operator, then it will do these operations on the elements and will do them element-wise for all of these operations. Therefore, we need less space for temporary arrays or vectors. And then it can just look at the first elements, do the calculation, and then store it in our result vector, which makes it more efficient. Oops. So we see from the before version, we had 2 milliseconds up to 25 milliseconds. And in the new version, it went down to 900 microseconds with a maximum of here 6 milliseconds. So this is a nice addition to the syntax. And you can look it up. There's also dot macro that will try to convert some of your expressions, so you don't have to put the dots in between. Now we've looked at things that we can measure with memory allocations. So we've measured the time. We've looked at profiling of memory allocations. What we can also further do is do further performance measurements on the machine that we are using. And in modern CPUs, they allow you to do some measurements of internal metrics. And there are some tools to read out these metrics. Therefore, you can see how the machine is behaving while it is running your code. In this case, we are using this liquid tool that has implemented these measurements for certain, for a list of different machine types, CPU types. So, and there is a liquid.gl wrapper that helps you to do it from Julia. And in this case, we have a matrix addition. So we iterate over the rows and columns of our matrix and add the values. And if we think about how many operations do we really do, then we see there is one floating point operation per element in the matrix. Therefore, our total number of floating point operations would be then the number of columns times the number of rows. And it's then a nice way to think about what should happen in your code, how should it behave, how many operations should there be. Therefore, have an inner model of what you expect, what should happen, and then you can also measure it. And in this case, we are using Liquid. We are doing this initialization of our arrays, and then calling this perfmon macro with the name of the metric that we want to measure, and then our function call, and then we get out these values. So there are two boxes here, two little tables. The top one are the raw counters, the raw values that were measured from or read out from your CPU. Therefore, we have the clock, the number of instructions that were actually executed. And then here we also have the number of floating point operations. And it also has some derived metrics where it has some little formulas internally. And we also see this runtime here. So we have here 3 milliseconds. And then also performance metric of floating point operations per second. Therefore, just the number of operations divided by the runtime. And we see here, if we measure it, it matches the our model. If we give in matrices of 1,000 times 1,000, then we have a million operations in the end. We can list the available metrics that Liquid provide us, and these are the low-level metrics from your CPU. And these are then groups of counters that are read out, or metrics. And here we see we have, for example, a lot of memory metrics with the caches, and also some energy metrics. Therefore, we can have these internal metrics that help us to reason about the behavior of our code. We can take a look at the behavior, and then we can also use these to figure out what is happening, where could be a bottleneck, and then do a measurement before and afterwards to compare how the metrics changed. And often these derived metrics are then more meaningful. They're easier to understand than the raw values that Liquid are giving us. And these performance counters have a low overhead because they don't interrupt your code execution. It's just setting up the measurement in front, then executing, and then reading out the counters from the CPU. Let's talk about memory layout. where we'll also see how we can use one of the other metric groups. And here we see the similar code matrix addition, but in two versions. And in one version, we are first iterating over the rows and then in columns to access the elements. And in another version, we are first iterating over the columns and then over the rows to access the elements. And as we see here, it's basically the same algorithm. It's just a different order of things. But we will see that one could argue it's doing the same. It should take the same amount of time, but if it's running on a real computer, then this is different. So as we see here with the mat@call version, it's taking 4 seconds. And our benchmark macro also did only 2 samples because it decided, okay, 4 seconds, maybe the user doesn't want to wait that long. I'm not doing that many samples. And with the other version, we see it only takes 56 milliseconds. So this is substantial difference in the runtime. And the benchmark also did 88 samples. And what we can do is we can use Liquid to do a measurement on the L2 cache metric. Therefore, there is some caching involved between the CPU and the memory, where some of the data that is cached in between. And we see that in one version, the L2 cache has a data transfer volume of 52 gigabytes. And in the faster version, we have only 2.2 gigabytes of transferred data in the cache. Therefore, the cache in one case can far better be utilized and work and spare us the memory transfers just because of the order of requests in our array. And the reason for this is how the cache is implemented. Therefore, we need to understand how the cache works to make sure that our algorithm is doing it in the right way. And if we have our matrix data structure, there are basically 2 ways to store it in memory, because memory is linear. There's the row major order and the column major order. And we see here that it's simply depends on the order of elements, how they are stored in memory. And as we see here, if we have a matrix in C or Pascal, it is stored in row major order. And in Julia, Fortran, or MATLAB, it is stored in column major order. This is just a specification of the how the language is generating the code and storing the data in memory. But it makes a difference on which algorithm is faster. And if we have a cache, this is a little piece of memory in between the CPU and the large main memory. Therefore, if we request some data from the main memory, it can be cached in the cache. And it will always cache not only one element, but we are talking about cache lines. This is simply because transferring a complete cache line from main memory is more efficient than singular values. Therefore, if you are accessing a value that is not in the cache, it will request the complete cache line and put it inside of the cache. Therefore, in one case, in the slower version of our algorithm, we are requesting one element, and the computer is putting a complete cache line in the cache, but we are not using these elements, but we are jumping to a different place in the main memory. So it has to request another chunk of main memory into the cache. And in the more efficient version, there we are accessing the first element and then also the second element and third element and so on in the cache. And since the elements are already in the cache, it's way faster than going then to the main memory for the second element. Just because of how the elements are stored in main memory and how in the order of how we are accessing them. Therefore, the cache fetches complete blocks of memory. And there is even automatic prefetcher. Therefore, if we are starting to fetch some portion of the data in our array and we are going linearly through this memory, the cache will already request the next chunks of data from main memory, even if we haven't requested one of the elements in this chunk, because it detects order of our memory accesses and then already request the next data blocks. So they're already there when we want to access them from the cache. Therefore, we see that just the order of memory accesses is already so basically changing how our algorithm behaves to how our machine is working to improve the performance. So we can make sure that our CPU machine is working as intended, is to get the best performance that is possible.
What is small math here? What is it?
That basically depends on the size of the cache. As explained, if it fits in the cache, then this is no problem. But if it doesn't fit in the cache, then it has to go to main memory, and then it is the question is about the order of the elements. For example, we have a very small matrix that fits into one cache line. Then if we request the first element, it doesn't really matter which one of these elements we request next. But if we have to jump around, then it has to request more of the cache lines. And we will take a look at how the hardware is, or how the cluster is built. Because with a better understanding of the hardware that is used, then we can also have better decisions in how we use the hardware and increase the performance. And this is a very coarse overview, so it's only a few slides. And we start at the coarse grain level when we are standing in front of the machine. And in the machine, in this case, is our cluster in Paderborn. So this is how it looks like. It's similar to the Ramses cluster. I mean, all of these clusters look the same. We have some racks where the CPUs and nodes are stored. Then somewhere in the case of water cooling, colder water is going in, warmer water is going out. We have to put some electrical energy inside. Then there's some networking going on. So there's the network cables that go on the top here and connect everything. So it's basically a very large water heater. And if we open up a door, then we see here we have these compute blades. And then there's also on the other side of the rack, there's also some networking hardware. And we see here some pumps for the water cooling. In this case, this is one one water cooling circle inside of the rack, and then it's connected to the building. And we also see here we have this compensation for the difference in water temperature. So if the water temperature rises, then the water takes a larger volume, and this has to be compensated. And this is how one of these racks look like. And if we take out one of these blades, then it looks like this. In this particular case, this is basically like a large pizza box. And in this case, we have 3 machines in one blade. And we see here there's some networking hardware, and then there's the cooling going in between the CPUs. Then we see there are 2 CPUs beneath here. So here's one and here's another one. And so we have one compute node here, and there's also some main memory. And if we take off the cooling hardware here, then we see that here we have our CPUs and the main memory. And if we take even of this heat spreader here from the CPU, then we see there are even multiple chips on the package of one CPU. So it's modularized for the production of the CPU. So you can imagine there could be cheaper CPUs with less of these CPU core chips, and then it would be a different model of the CPU. In this case, we have one chip in the middle, which is for the I/O, for the memory transfers, and so on. And we have these 8 little chips with the CPU cores. And in the schematic, it looks like this. We have our 2 CPUs in one node, and they talk to each other over the CPU interconnect. And then we have the main memory connected with 8 channels per CPU. And we see here our CPU cores in red. And in between, we have our caches. So the caches are also on these little CPU dies. And this already also explains why these caches are so important. So we have, for example, one core, and they are level 1, level 2 caches that differ in size and the latency. So if our CPU is doing some instructions that request memory, then the request goes into the L1 cache. If the data is there, then we get a response in maybe 4 to 8 cycles. If not, the request goes further down, and here it then would take 12 cycles. And in the 3rd level, it would take 46 cycles to get back to the core. And in this time, if we request synchronously some data, the CPU will wait for the data. So in these cycles, it can't compute anything because it needs to wait for the input data. This is basically a wasted time with waiting for data. And if it's also not in the L3 cache, then it can take then in the hundreds of nanoseconds to get the data from the memory, because then it even has to go out of the chip into the other chip, out of the CPU, through the lanes onto the memory chips. And then it has to look up the data in the memory chips, and then the response has to go all the way back. This is why it takes so long. And this is why we saw that if we make good use of the caches, it can only take a few milliseconds to run our memory addition. But if we misuse it, then we have a lot of data going back and forth between the caches. And this takes a lot of time, and therefore then we have 100 times larger runtime of our little application. And we also see that we have this large cache hierarchy with 3 caches, and the top cache is 32 KB, and then the L2 cache is 512 KB, and the L3 cache is 32 MB per CPU core chip. And this is the L3 cache is then shared between the CPU cores. And this has something to do with how the caches are actually built on the chip. So this cache is faster, but it's also more expensive, also from the area that is used. Therefore, it is smaller. And then the L2 cache is larger, but therefore slower, and so on. Therefore, if we make good use of the caches by having a certain pattern of accessing our data, then we can reduce the memory transfers and therefore only get the data that we need from the caches, and this improves the performance. So we see that on one side we have computations, this is what we actually want. On the other side we have memory transfers, which are kind of a side effect of what we want to do with our calculations, but we need to do them, but they are, in comparison to the calculations, they are slow. So we need to transfer the data into the CPU, do our calculations, and then at some point maybe also the results back. But in between we want to have as few memory transfers as possible. And this cache hierarchy is one way to achieve this, because there's this difference in performance of calculations and the memory transfer speeds. Now, one other feature of CPUs are SIMD instructions. And these are so-called single instruction multiple data instructions. So before, you can imagine if you do one operation in one instruction, then you need to specify some data. And this is scalar data because you're only doing this on one element. But there are also extensions to the CPUs where you have one instruction that doesn't do the operation on only one scalar value, but we are talking about vectors of values. So you have one instruction, but you do the operation on multiple elements. And internally, then vectors and vector registers are used. Therefore, the CPU has to be extended, and also the memory bandwidth has to be extended to provide the CPU with enough data, so it will be worthwhile to do this. But in the case of the larger extensions here, we can even have up to 8 doubles of values per vector. And this improves the performance of our operations. So we are not doing one operation at a time, but suddenly we're doing 4 or 8 operations at a time. This also has an effect on the frequency of the CPU. So if you're doing scalar values, then you can clock higher, because then less work is done on the CPU, and then also it needs less power. And if you're doing more work at the same time, that it's a good thing, but it will clock a little bit lower. So, but let's not go in this thing. Let's think about the achievable performance. And this is a thing in HPC or performance optimization, where we think about what is even possible on a certain machine. We have an algorithm. We can think about a model of our algorithm, what it is doing, how many floating point operations do we need to do to achieve our calculation. And then the question is, what is the maximum performance of our machine? And can we, if we implement our algorithm in our code, can we achieve this performance? And we can do a little model theoretical computation here. If we have one CPU core, and in this case, we are doing 4 operations per cycle because we are using these vector instructions. And we have 3.6 gigahertz of a clock. Then we could achieve 14.4 gigaflops of floating point operations of performance on one core. And if we are using multiple cores at the same time, then we can, in our case with 64 cores, they will clock a little bit lower, as explained, but we will achieve 700 gigaflops of theoretical performance. Oh no, this was even a scalar. Okay, so this was the 4 flops come because we are counting 2 floating point operations. So there are certain instructions that are doing an addition and a multiplication in one instruction, and we can do 2 of these in one cycle. This is why there's a 4. And exactly in here we take the 16 flops because then we are using the vector. And this way we can then achieve an even higher theoretical performance. However, this is in the ideal case. This is the case when we are only doing these operations and nothing else. So there are no memory transfers, there are no other control flow instructions and so on. So this is just the peak that is theoretically possible, but will be usually never achieved. But we can, and Julia is trying to use these vector instructions to achieve a better performance, but it's not always possible. And there are some ways how we can help Julia to prove that it's possible to use these instructions. And to get a better performance. So in this case, I'm using this inbounds macro that tells Julia to not check if our array accesses are out of bounds, so out of the memory of the array, because I'm very sure that it will be fine. So usually it will always, for safety reasons, check this. But in this case, I'm quite sure that we are not going out of the size of the arrays. And therefore, we have our vector dot function that again multiplies 2 vectors. And there's this add SIMD macro in Julia that asks Julia to improve the performance by not checking some of the things, not checking some of the requirements that holds it back from doing these optimizations. So in this case, we are simply saying that all of the iterations of this loop can be interchanged. So it doesn't matter in which order these iterations are done, which is not always the case for loops, because sometimes in one iteration you need some values that you computed in a different iteration, and then the order matters. And this is a thing that is very hard to prove in general. Therefore, with the add SIMD, we can nudge it into doing a better optimization. And there's also another package called loop vectorizations, loop vectorization with an add turbo macro that is doing some macro magic to even better optimization. And if we measure it, then we see we have in our first version, we get 890 microseconds of runtime. In our SIMD macro version, we got an improved performance of 190 microseconds. And with this turbo version, it was quite similar, so there was not much of a difference. But there's another possibility here when we are loading this linear algebra package, then it is not instead of using our own version where Julia is doing the compilation, but in this case we are using this dot function that is already prepared, and in this case it will use some libraries that come with Julia or installed on the cluster, and there is for this linear algebra operations, they are hand-optimized versions that also take into account the memory accesses and so on. So this is always a good idea to use these pre-optimized versions in these BLAS libraries. And here we see that there's an even better performance of only 15 microseconds. Therefore, it helps, but it's not as fast as some professionals spending some days filling around with the assembly to get the really best performance out of the machine. Before we, okay, maybe we skip this. Now HPC is about parallelism because at some point you can only get to the top of the performance on one core, and therefore we want to do more work at the same time to reduce the runtime. And what we've seen is, in this case, with the SIMD instructions, with the vector instructions, we are doing the same operation on multiple data elements to do them at the same time. So here we are doing the parallelization on the data level. There's also some parallelization done by the CPU just by design. So this is nothing that you can influence, where it looks at the instructions and then decides, okay, I can run these instructions in parallel. But then we also have these other levels of parallelization. So we can use threads and have do calculations in multiple threads. This will then be the topic in the afternoon. And we can use multiple processes and even scale to run our calculations on multiple nodes. Okay, this is just a summary of how we can improve the performance. And for that, we need to have a base for our decision making. We do the measurements. We see where's the code that really matters for the performance of our application. Then we can measure some metrics to figure out what is the behavior, why is it so slow, and then improve our code, and then measure again to see that it really helped. And for this, we also need to understand how the hardware works, how it is structured, so we can achieve a good performance that is possible on the hardware. And in the end, also the parallelization matters, that we will see in the next sections. But that's it for this section. Do you have any questions?
I must admit, I think I would still be pretty lost if I want to try and improve the runtime of my Julia code, simply because there are so many options, and not in all of these cases, it's obvious for me where specific case could apply and where not. Would you say the best solution, if like me, you are not really sure what to do, is first of all rely on packages provided by people who know what they are doing, like the linear algebra package, and see if that is enough?
In general, I like to do things myself, but if you want a good performance and not spend so much time fiddling around, then absolutely. As explained, these BLAS operations, these are then optimized for the machine and even better than Julia could do it. Therefore, if you can figure out in your algorithm that the most work is done by these operations, and then you can reduce whatever you do to these operations, and then let do the number crunching be done by these specialized libraries, then you will also achieve usually a good performance. You can still measure it. You can still see, okay, it should be only these matrix multiplications, and they should be quite fast on the machine. And then you can do a measurement and see, okay, am I doing these many floating point operations as should be done in this time on the machine, to make sure that that you actually achieve a good performance, and not. I mean, it could be that you do all these things and then you figure out, okay, there's something happening in the initialization, and you could think 2 seconds is already good, but maybe the actual computation just takes 50 milliseconds, and the other time is spent somewhere in a problem. So for the order of things, if you have some problems in the memory allocations, or you have some problems with the types in Julia, then these are already introduce so much overhead in the performance that these are like the big problems that you want to look at, and that will also then will have a good performance improvement for your application. And then further, you can see if there's no low-hanging fruits anymore in the Julia code, in the part where Julia is doing the work for the compilation and so on. Then you could further look at what is the performance I'm doing right now, what could be possible, what am I thinking of, what is my algorithm actually doing, what calculations are actually done, and is my application using its time with memory transfers, or am I doing the calculations that I actually want to do? And really, as we've seen, the memory allocations are not that hard to figure out what is happening, and then you can think about how to reduce them, which will have a very good performance improvement. Okay, then let's take a break.